Okay, good morning. Okay, our next topic is construction of push-down automata for the given uh, grammars. Okay, here now we need to construct push-down automata for the language. L is equal to a power b power n, where n greater than or equal to 1. So the language L is equal to AB a square b square a cube b cube a power 4 b power 4 and so on. This is the language. Now we need to construct the push down automata for the language L is equal to a power n b power n. So actually the push down automata contains a finite control along with the input alphabet. So I will take the example as double A double B. So of course it is triple A triple B also okay. Triple A triple B and the input tape and stack. Input tape and stack. It is a stack symbol. So actually in the given grammar, we need to in the given grammar we need to push a power n and we need to pop b power n. Okay. So first of all, the production delta of now the finite control is in the state q naught. Delta of q naught, comma the input tape is a, comma z naught. If if the push down automata in the state q naught, if you have the input a and the stack alphabet is z naught, then we need to push into the stack. So it is q naught, comma az naught. So here the next diagram is a z naught. So it's completed. So it goes to here. Next again q naught a delta of q naught a that is equal to q naught, comma a. Again I need to push a in the finite automata. So it is a here. And next input tape contains the alphabet as small a. Find delta of q naught, comma small a, comma a. That is equal to it is q naught, comma a only. And next we have the symbol b. So delta of q naught, comma b, comma sorry a, that is equal to if the input tape contains the alphabet as b, then we need to pop the symbol from stack. Okay, so then it is here q1, comma epsilon. Q1, comma epsilon. So here we have 3 A's. Now for single B we eliminate single B here. Next, now the state is in Q1 only. Next production delta of Q1, comma B, comma here A, that is equal to again we have the input B and the top of the stack is equal to A. We need to remove the top symbol again. So it is delta of Q1, comma epsilon and delta of q1, comma next it is the last symbol q1 comma b comma a is equal to q comma epsilon. So it is also eliminated. Third b is also eliminated. Next we have delta of q1 comma z comma z naught is equal to qf comma accept qf comma accept. This is the final pushdown automata for the language L is equal to a power n and b power n. Okay, it is deterministic pushdown automata because here we know how many characters we need to push and how many characters we need to pop. So next, coming to next question, uh, construct a pushdown automata for the language L is equal to uh, okay, a power n c c b power n. So here we need to push the all the a's comes before a, and we need to pop all the b's after c, and we don't do any operations if the input is small c. Okay, the productions is nothing but delta of q naught comma a comma z naught is equal to q naught comma a z naught, and again next q naught comma a is equal to q naught comma a, and delta of q naught a is equal to q naught a. Next step we have c here. So next delta of q naught c small a is equal to q naught a. Here, if the input a comes, we need to push into the stack. If the input b comes, then we need to pop from the stack. If the input c comes, then we don't do any operation. Here, no operation required. Okay, here no operation required. Okay, next we need to perform the next operations. So it is delta of it is q1 comma b comma small a is equal to q2 comma epsilon. Again we have delta of q2 comma epsilon is equal to sorry, q2 comma b comma a is equal to q2 comma epsilon. So on the final q2 comma b comma a is equal to q2 comma accept. It is the pushdown automata for the language L is equal to a power n and a power n c b power n. It is also deterministic pushdown automata because we know the number of push operations it is a power n and number of pop operations b power n. Okay, if I take L is equal to a power n, L is equal to a power n, next a power m, L is equal to a power n and a power n plus 1, a plus 1. Here I don't know exactly the half part of the given string. Then the grammar is said to be non-deterministic pushdown automata. Okay. Next. Okay, now the question is S tends to A, S, B or epsilon. So we need to find the grammar or the language generated by the given productions here. The first string is s tends to lambda, and second string is s tends to ASB. In place of s, again I need to place lambda, so it is ABAB, and again s tends to ASB. Again s is replaced with ASB, and it is lambda, so it is AA and BB. So here the language is equal to lambda AB double A double B and triple A triple B. So it is okay. So it is the language L is equal to A power n and B power n. So language L is equal to A power n and B power n. Okay. So it is A power n and B power n. We will go with next question. Okay, here we have some objective questions or some 2 mark questions which will help you to find the answers also. Okay, the first question, it is a define context-free grammar. Actually, we know the context-free grammar is a grammar which contains the 4 tuple symbol. It is a VTPS, where V is the set of non-terminals and T is the set of terminals, S is the starting symbol, and P is the productions. Okay, coming to this, given these productions, and we need to find the language generated by the given grammar. Okay, here again it is missed. Okay, it is B tends to small b. This production is missed. Okay, coming to left linear grammar. A grammar is said to be left linear grammar if all the productions in the given grammar is like non-terminal tends to non-terminal into any number of terminal symbols. Here T star is nothing but any number of terminal symbols. It is nothing but it is a clean closure operation which contains A star is equal to epsilon A, double A, triple A, and so on. Okay, in the same manner, right linear grammar also, a grammar is said to be right linear grammar if it is in the form of non-terminal tends to any number of terminals followed by single non-terminal, non-terminal symbol. Okay. Next, what do you mean by parsing? Parsing is nothing but derivation or finding the string from the given grammar by using production rules. We are going to find a string, then the procedure is said to be parsing. Okay, derivation tree. The graphical representation of parsing or derivation is nothing but derivation tree. It contains root node, children nodes, and intermediate nodes also. Okay, here it is the derivation tree for the given grammar. S tends to AA, S tends to AA. Again, A tends to small a b, and B tends to small b, capital B. B tends to small a. B tends to small a. Okay, next one. What is an ambiguous grammar? Actually, ambiguous grammar is nothing but a grammar which contains 2 or more different parse trees for the same string. Then the grammar is said to be ambiguous grammar. Okay. Next, useless productions. Actually, for example, S tends to AB or capital Z, A tends to small a, and B tends to small b. in this given grammar, C is useless because C does not have any production here. So C does not have any production here. So C is a useless symbol. So here a production which does not affect the language is called useless symbol. Here the capital C does not affect the language as S tends to small a b is the language generated by the given grammar. And coming to what is unit production? Unit production is nothing but a grammar is said to be in production in the it is in the form of non-terminal tends to non-terminal. It is the capital symbol tends to capital symbol. Then it is said to be unit production. Okay. Actually, we learned this NTPS or VTPS. Okay. Here, the given grammar S tends to SBS. Okay, we'll see here. S tends to S, B, S. It is S. S tends to SBS. It is small a. Sorry. It is small a. It is small a, small a. The string is AB, AB, A. In the same manner, I'll draw one more parse tree here. S tends to SBS. It is A. It is yes, again SBS. It is small a. It is also small a. So the again the string is AB, AB, A. So the grammar is ambiguous. Okay. In the given grammar, in the given grammar, S tends to A, S, B. Again, S tends to have lambda. So it is AB. So here, S tends to ASB, S tends to epsilon is useful. Okay. If I take S tends to capital A production, and in A I have small a, capital A, and for A I have again small a and capital A, and there is no ending for capital A. Here in this grammar, there is no ending for capital A. So the productions which contains capital A is useless. So the grammar, the useful grammar is S tends to ASB or epsilon. The useful grammar is S tends to ASB or epsilon. Okay. Next, determine whether the grammar G with P has a useless productions. Okay, we'll see here. So here S tends to small capital A, again A tends to AA or epsilon. So these three productions are useful, and there is no capital B here. That's why capital B tends to small b, capital A is useless production. Okay, capital B tends to small b, capital A is useless production. Okay, and uh, here lambda or you can say it is epsilon also. Epsilon is a production which okay. Next, we already studied here capital symbol tends to capital symbol, so it is said to be in production. Okay, left recursion. It is also one of the important question. Left recursion is nothing but here A tends to AX before arrow mark and after arrow mark. If you contain common non-terminal symbol, then the production is said to be left recursive production. Here A tends to AX is a left recursive production because it continuously generate a tree which left. Okay, it is AX. It is left recursion. Okay, and how many types of normal forms we have? We have two normal forms: Chomsky normal form and Greibach normal form. Chomsky normal form contains non-terminal tends to non-terminal into non-terminal. and non-terminal tends to only single terminal. Coming to Greibach normal form, it contains non-terminal tends to single terminal into any possibility of non-terminal. It is N star. It is the syntax for Greibach normal form, and these two productions are syntax of Chomsky normal form. Okay. Okay. There are two types of normal forms. First one is Chomsky normal form, and second one is Greibach normal form. Actually, the normal forms are used to count the number of steps to produce a string from the given grammar. Okay. Next question. What is Greibach normal form? I already said that a contest-free grammar is said to be Greibach normal form if the all productions have the form A tends to single terminal and non-terminal possibilities. Here, a small a tends to terminal, single terminal. Here, x belongs to v star. V is nothing but it is a non-terminal set. So we here we will take all the possibilities of non-terminals. Okay. It is the representations of CNF and GNF. Okay. Coming to push-down automata, where I discussed the problems about push-down automata. In this again we have two types of push-down automata. First one is deterministic and the second one is non-deterministic. The example for the deterministic is L is equal to A power n, B power n, where n greater than or equal to 1. For example, if I take L is equal to W power R, W power R, where W belongs to A comma B whole power plus, then the language is said to be non-deterministic push-down automata, because here we don't know how much string we need to push and how much string we need to pop. So we don't have a unique production to perform a single operation. So then we go with multiple number of possibilities to create a deterministic push-down automata. Okay, here L is equal to A power n, B power n. Here we know the all A's need to push and all B's we need to pop. So it is deterministic push-down automata, and the below one is non-deterministic push-down automata. So it consists of a 7-tuple machine where q comma summation delta rho q naught z comma f, where z is the stack alphabet. Okay, and next. Okay, here we have a problem with push-down automata. Here we have a problem with push-down automata. It contains only one stack, right? So a language L is equal to A power n, B power n, where n greater than or equal to 1 is accepted by push-down automata, because it contains one stack for B and one input tape for A. For what happens if the language L is equal to A power n, B power n, C power n. So the language which consists of two conditions, here two conditions, right? number of A's is equal to number of B's, number of B's is equal to number of C's. So then we'll go with pushdown automata which contains two stacks. So it is a two-stack PDA. So it is a finite control and it contains one input tape along with the stack one and stack two, along with stack one and stack two. Here input tape stack 1 and stack 2. For the languages called A power n, B power n, C power n, all the string here double A, double B, and double C. Number of A's we need to push in stack A, number of B's we need to push in stack B, and now if number of C come, we need to pop one symbol from A and one symbol from B. So it is a working procedure of two stack PDA. If the number of conditions increase, then we need to increase the stacks also. So it is very complex. If it is very complex by increasing the number of stacks for different types of conditions. Okay, here Q naught comma A comma 0. If the state is Q naught, if the state is Q naught, A is the input symbol. If the stack alphabet is 0, here we have two operations. Whether it is go to Q1 state with 10 output and whether it is go to Q3 state with epsilon. So the grammar is said to be non-deterministic pushdown automata. Non-deterministic if it contains two or more productions, two or more outputs for the given production. Okay. So here also construct PDA accepting A power n, B power 2n where n greater than or equal to 1. Here we have a condition on A power n and B power n. Here we have only one condition. So it is sufficient to use a single pushdown automata, single stack pushdown automata. Okay, but here we need to push two A's for every single input of A. So for example, Q naught double A 4 B's 4 B's. If we have a stack here, so if the input is A, so we need to push two A's. Again, if the input is A, if we will input here for input B, we need to pop for all 4 B's, we need to pop all 4 A's. So it is the example for pushdown automata. For the language L is equal to A power n, B power 2n. A power n, B power 2n. Okay. Next, here the language L is equal to A power m, B power m, C power n. Here we have condition on A and B, and we don't have any condition on C. So we need to push A's and we need to pop B's, and we don't do any operations on C. Okay. Here also the language L is equal to A power n, B power m, A power n. So we need to push A's. If B comes, then we need to we don't do any operation because we don't have any condition. Then we need to pop the A values after. Okay. Next one. So it is the syntax of Chomsky normal form and syntax of Greerback normal form. Okay. Okay, ma.